Hello, so welcome to Lecture 3, Module 2. We're going to talk about op amps. So op amps are, op amp is short for operational amplifier, and what they mean by operations is that they're talking about math operations. So if you have voltage signals and you want to add voltages together, you can't just twist the wires together. That doesn't work. If you want to scale them up, this is the most common thing to amplify a voltage signal. But you can also do things like calculus. There are op amp circuits for derivatives and integration too. Normally, you look for an op amp cookbook. There are books that are titled that. Manufacturers will have common circuit design. So you don't normally have to design something for an op amp. If you know what the math you want to do, you can look it up. One thing to remember with op amps is they're not good for high power. So you don't want to drive a great big speaker or a motor or something like that with an op amp. They're really for signal manipulation. So good for sensors, good for data acquisition. The op amp has an external power source, so it doesn't really have any influence on the sensor in the most of the time, the way we use them mostly. So here is the op amp schematic. The three main parts of the op amp, there are two inputs. The inverting input has the minus, the non-inverting input has the plus, and then the output. And you'll often also see the little whiskers here that show the power supply provided to the op amp. You need that for any op amp circuit, but for the theory it doesn't matter so much, so they often leave them out in theoretical schematics. Non-inverting is a double negative, so my worst joke is that this one should be called the verting input. There you go. Feel free to use that. So op amps are neat systems, and they have a really high gain. You can analyze them from first principles that way, but the way they're almost always used is with a feedback where the output is fed back to the inverting input, or at least one of the inputs, usually this one. And with that, we get these two rules for op amp analysis so that we can use node analysis techniques. So the first rule is that if there's feedback, then the input lines here have zero current through them. So the current through there is zero, so when we do node analysis, there's no current here to worry about. And then the other rule is that the feedback makes the voltage at this input and this input be the same. So here where the non-inverting input's grounded, so it's at 0 volts. So that means we can assume that this whole node is also at 0 volts. So if you use those two rules, then you can use node analysis to find the output voltage. You can't assume that there's no current coming out of the op amp, and that's what would that's why we need some extra rules, because there's no Ohm's law or anything. So we don't know how much current comes out of here, but we can use those two rules to get a system of equations to solve. Here's an example of using that rule on this inverting op amp circuit. So the non-inverting input is grounded. So node 1 here is at 0 volts from this rule. These match. V out node, this node voltage is what we're solving for, and we're given Vi, the input. So if we know this one, we need to solve that one. We know this is 0 volts, so we just need one equation. So we can do Kirchhoff's current law on this node. It looks like this, VO minus 0, so VO minus the 0 here, divided by R2, that's coming in, plus Vi minus 0, Vi minus 0, that's coming in this way, divided by R1. Both of these coming in equals nothing going out, because we have 0 current there. And if we solve that one equation for the output voltage, we get this standard inverting op amp formula. So once you recognize this circuit, when you see this configuration, you know it's the inverting op amp, so you don't have to analyze it. But don't assume, make sure you're looking at the right circuit, because there are lots of different circuits. So an inverting op amp has a negative sign, so the output voltage is negative if the input voltage is positive. So sometimes people don't like that for sensors with DC values. For AC kind of signals, it often works just fine this way. And this is the gain, the scale factor, negative R2 over R1. So with two resistors, you can set the gain to anything you want, as long as you don't mind the sign change. If you do mind the sign change, if you want your output to be positive and your input is positive, you can use the non-inverting op amp circuit. So this is a different circuit. So again, you have to look and see how it's set up. Here we have the input connected to ground. Still two resistors, a feedback resistor and this resistor connected to ground on the inverting input. If you do the analysis using those two rules, you'll come up with this, the output voltage 1 plus R2 over R1 times the input voltage. So the gain is still set by these two resistors. The big limiting factor with this non-inverting circuit is the gain has to be greater than 1. So you can only make VO bigger than VI because you can't have negative resistors here. So the smallest gain you could have would be 1. But it's easy to make larger gains. You can't use this for reducing, but that's what we often use voltage dividers for, as we talked about earlier. So this is the most common in our instrumentation class. The non-inverting op amp circuit is kind of the baseline that we start with amplification. The last circuit that is commonly used in instrumentation is the buffer circuit or the voltage follower. It's very simple. It just has one feedback, no resistors. Just connect the output to the inverting input and connect V in to the non-inverting. So it's kind of a special case of the non-inverting. But we have V out equals V in. So it copies the voltage. So it seems kind of useless because we've got V in here. We could just wire it up and get V out. So it's usually used when you need to isolate the circuit, because remember this is powered separately. So you don't draw any current from whatever's hooked up on the V inside. So it's commonly used with voltage dividers reducing the voltage, and it gets rid of the loading error because there's no current going through here. And so if your system needs a voltage divider to reduce the voltage, but it pulls some current, the buffer is a good solution to that. So you'll see this in lots of places. It's worth pointing out that you can do lots of things with op amps, and there are some common configurations, like these 3 op amps configured this way are called an instrumentation amplifier. That's covered in the book. And then there are integrated circuits that combine op amps together. This is a circuit for the AD623 amplification chip, where a single resistor sets the gain. So RG, you can calculate what resistor you need if you know the gain you want. So rather than 2 resistors, it's 1 resistor, and it has some other good properties compared to using a single op amp. And then op amp cookbooks are really important. You could probably find them all online these days. Back in the old days, you would actually have a book. But manufacturers want you to buy their op amps, so most of them will have circuit collections you can use. So this one is from National Semiconductor. There's the non-inverting and the inverting, difference to subtract voltages, and summing to add voltages. So look online for common circuits to use with op amps. Well, that's about it for op amps today. Hope you learned some things, and don't forget to take the quiz on Brightspace. See you later.